see. And so that lets us know that there's a planet going in front of it. Astronomers tend to favor this method more because it can tell us more about the mass, the atmosphere, the temperature. But it normally works with more massive planets, and even then it only blocks about 1% of the light. The Kepler mission is a spacecraft that was launched and operated by NASA. The mission searches for extrasolar planets, preferably ones that are in the habitable zone, but not all of them. It uses the transit method, but it's unique in that it finds smaller planets, ones that are 30 to 600 times less massive than the transit method normally picks up. So this right here is the Kepler field of view. My objects of interest are going to be in the constellation Cygnus, which is right here. So this is one of the planets that I have been working with as well, and this is Kepler 21b. This is the transit light curve. It is basically over the intensity versus the time, and this one's in hours particularly. As you can tell, this is the star's normal intensity and then brightness, and it drops down, and this is over the time that the planet is transiting in front of that star. So Exoplanet Discovery. So there's been 4,609 discoveries so far. Only 1,706 of those are confirmed, and 962 of those are Kepler planets. These are always changing because we discover more, and planets will go from being a candidate to confirmed. And to confirm it being a transit, confirm it doing the transit method, it has to transit, we have to measure it 3 times transiting around its star. So when we're using a ground-based telescope and we get light from other stars and galaxies, a lot of times our atmosphere, when it goes to our atmosphere, it will become blurry and distorted. Adaptive optics works to remove these obscured effects that happen because of our atmosphere. As you can tell, this is a before and after. These are some before and after pictures. It's a lot better afterwards. This one, there's actually 2 objects, and before you can't even tell that there's 2 objects in there. So AO systems also can distinguish blended stars, which normally happens when there's a really bright star next to a faint one. So it's ideal for binary star systems. Binary star systems is when there's a solar system with more than one sun in it, kind of like if you guys have ever seen Star Wars, Tatooine. And so this right here is taken from the it's at Caltech, and it's a robotic laser AO system. And this is after the AO, and as you can tell, there's a really bright object right here and a smaller one. When they subtracted the bigger, the brighter object, you can tell that there's actually another star right there. Kapow. So Kapow is an adaptive optics system that's located in the San Gabriel Mountains. It's a 1-meter telescope that has an adaptive optics system on it. And they measure visible as well as infrared light. So in order for Kapow to be able to make changes using the AO system to create sharper images, the object has to be bright enough. So I decided to do my Kepler objects of interest on stars that yield magnitudes of 11 or brighter. If you can see right here, this is the guide star magnitude versus the Strel. The Strel is the ratio of the light aberrations that happen from our turbulent atmosphere over the image quality. So you can tell right here, the green is the infrared light and the red is the visible light. I know it's kind of opposite, but so as you can tell right about here, it starts to drop off, meaning that it's not really going to make much of a difference to that image by using adaptive optics. So I decided around 8, I couldn't really find that many that were brighter than that, so I decided to make my cutoff magnitude of stars that are 11 and brighter. So the benefits of adaptive optics on Kepler objects of interest. It can create cleaner images. It can help us better understand the environment in the solar system as well as outside of the solar system, and if there's solar systems that are similar around it. Can rule out false positives. It can separate these merged stars and recognize binary and multiple star systems. Hopefully, eventually, maybe even viewing the light from a brighter planet where the star is overpowering it, and used in conjunction with the transit method. So I was able to get information on these Kepler objects of interest by doing database searches. And this was the output of it. As you can tell, there's a lot of data right here. This right here is the magnitude. The blank area are planets that aren't confirmed. So I was able to look at all the magnitudes and pull the planets that had magnitudes that were under 11. So this is my list of target objects of interest that I hope that the adaptive optics system can use. They go from the brightest one having a magnitude of 8.224, which is Kepler 21b, to Kepler 10c and 10b, which is 2 planets in the star system. And that one is 10.961. So the Simba Query allowed me to pull and get images of a lot of these stars. I want to be clear that these are the images of the stars, not the planets. We can't really get images of the planets. And the Simba Query uses the Aladdin Sky Survey, and that uses a bunch of different telescopes to get the images that it needs. So all of the pictures are coming from different telescopes, but some of those include like the Planck telescope, the 2 mass, like a lot of those ones. These are the images of a lot of the stars that I got, some of the better ones. Kepler 13 is a binary star system that only looks like there's one star right there. A lot of them are blurry, and there's objects around them that are really close to them that kind of look like they're blended together. Adaptive optics would definitely help give us a better view of these images. And for images that I wasn't able to get on there, I use CDS, and this is like a broader sky survey of them. And Kepler 410 is a binary star system with 2 stars, and this one right here, as you can see, this is more up close. It looks like one star, and it's blended together, so adaptive optics would definitely help us be able to distinguish the 2 in an image. So this is my list of the planets in our solar system. This is the radius is in Earth radiuses, so it's the amount of Earth radiuses. And astronomical units is the semi-major axis. So 1 astronomical unit is the distance from our Earth to the Sun. And so, as you can tell, and I compared them with the planets in our solar system. As you can tell, the astronomical units are very similar to each other. And this is a logarithmic scale of the radius versus the semi-major axis. What I noticed from a lot of these planets is that they're all very big. They're a lot bigger than Earth. They're like planets with large radiuses that are very close to their sun, which is kind of different from our solar system, because our solar system it kind of goes in a fashion where it's like the smaller planets are closer to our sun, and the bigger ones are on the outer. I mean, it's not totally in order that way, but and so it's very different from our solar system, because theirs are big and near their sun. I was able to calculate their habitable zone, and the habitable zone is the distance that makes it livable. Not livable, but it's not too hot, meaning that it's not too close to their star, and not too cold, meaning that they're not too far away from their star. It has to be like the perfect area in order for there to be things like liquid water, and similar to Earth, basically. And the majority of them are not in the habitable zone because they're too close to their sun, so yeah. But a few of them were, but very optimistically, like best case scenario as well. So they're very different from our solar system. But I hope to be able to have, to use the information that I've gathered in my target list to have Kapow do a follow-up on these images, and In the longer scale, I hope that it will help us learn more information about these solar systems, as well as finding out in a whole that general area. A lot of them have very similar solar systems, so it shows that they were formed in the same area, and they all follow a general pattern of being very similar, and I hope that adaptive optics will help us gain more information and better quality images on these objects. And I'd like to thank my advisor, Dr. Scott Severson, for being like so good working with me, and my mom and my sister.
Yeah.